Good morning and welcome everyone to today's talk from Li-Qiao Xia. Li-Qiao received his bachelor degree in applied physics from the University of Science and Technology in China, or USDC, in 2019. He then came to MIT in 2020 as a graduate student, and is working in the group of Pablo Jarillo Herrero. During his PhD, Li-Qiao worked on intrinsic 2D magnets as well as on graphene-moiré materials. In his talk today, Li-Qiao will tell us about an exciting new avenue in moiré materials, where by combining two moiré lattices rather than just a single moiré pattern, one can form more complex and rich structures. Li-Qiao will focus on one especially interesting system called helical trilayer graphene. Just a couple of housekeeping rules for today's questions. So feel free to ask questions in the chat during the talk, but we're going to reserve all the questions for the Q&A session in the end. The talk will be 25 to 30 minutes, and then we'll have a 15-minute Q&A session. During the Q&A session, I will moderate the questions from the chat or from the Q&A, where you can place your questions, and you can also raise your virtual hand, and I'll give permission of speech, and you can just talk freely. So that's it. So with this, let's welcome Li-Qiao. Li-Qiao, the stage is yours.
Thank you, everyone, and it's my great pleasure to virtually be here today and share you some of our recent results on this new moiré structure, helical trilayer graphene. As I'll show you, it's a moiré platform for strongly interacting topological band. So before I started, I would like to first thank my collaborators, Dr. Avraham Uri, Dr. Sergio de la Barrera, and Supervisor Pablo Herrero, and also Professor Liang Fu. Part of the measurement is done at David Goldhab and Gordon's group at Stanford University, together with Dr. Aaron Sharp. And our theory is done by Patrick Lewis, Yves Kwan, especially Dr. Trisha Devaku, now professor at Stanford, and Zian Zhu. Our beam crystals are from Kenji Watanabe and Takashi Taniguchi from NIMS, and the sample fabrication is done using the shared facilities at MIT.nano, CNS, and MIL at MIT, and also our various funding resources. So I would like to start my talk with showing you monolayer graphene. This is mostly studied material in our lab, and it's composed of carbon atoms formed in this honeycomb lattice, and it can be isolated by using a Scotch tape. So starting in 2018, pioneered by our group, there is a new degrees of freedom has been introduced into this system, which is a twist angle. So basically, if you put another monolayer graphene on top of the first layer and rotate it with a small angle, you will see this emerging the moiré pattern. You can see this area with A stacking order and also AB and BA stacking order. This A stacking order form a triangular lattice. We call them moiré superlattice, and the distance between two nearest A side is moiré lattice constant AM, which is equal to the A0 over theta. Here A0 is lattice constant of graphene, and theta is a twist angle between the two layers. So the way to think about this system is introduced in 2011 by Bistritzer and Alan McDonald, where they use the so-called continuous model, where they capture that the low energy physics of this moiré superlattice is actually dominated by this moiré potential, which is a periodic forming this moiré lattice, and they can work out this moiré band structure in this moiré Brillouin zone, and what they find that is close to the angle of 1.1 degree, the first moiré band become extremely flat, where the kinetic energy of the electrons is quenched and opens all the possibilities for all fascinating strong correlated physics. So this angle 1.1 degree is so-called a magic angle, and is first realized in experiment in 2018 by our group, and indeed there is correlated insulator, and very surprising, there is superconductivity emerging in this magic angle twisted bilayer graphene. So here, what I'm going to show you today is to one step over this. We add another monolayer graphene on top of this twisted bilayer graphene, and in a helical way. So these 3 layers of graphene sheet are rotating in the same direction by the same angle theta. So we call it a helical trilayer graphene. And the motivation is also quite straightforward, is that whether we will see new correlated physics in this new structure, new system. So so first we want to understand the system by looking at what is the structure. So here, instead of showing you the atomic structure, I'm showing you the moiré structure. So here's the orange and the purple dots as the moiré AA sites of layer 1, 2, and layer 2, 3. So both of them form this triangle lattice, moiré lattice. And because it's a helical structure, these 2 moiré lattices also rotated respect to each other by the angle of theta, which form this even larger supermoiré lattice, which I labeled using these 2 arrows. And this supermoiré lattice constant is equal to moiré lattice constant, AM, over theta, which is basically the A naught over theta squared. So a few simple observations about this system. The first is that the whole system preserves the C2Z symmetry. And second, because these 2 moiré lattice is actually misaligned in space, so the whole structure is actually not moiré periodic. So it's actually from a so-called moiré quasi-crystal, which the idea is firstly introduced in this paper published in our group earlier this year. Here we adopt this definition of this moiré quasi-periodicity by it means that the number of the primitive vectors is larger than the number of the dimensions. So to understand this system, because it's moiré aperiodic, we cannot directly apply the continuous model introduced by Bristraser and McDonald's. However, we still can use a so-called moiré periodic approximation, and this is based on this scale separation. Since we are all working in the small angle regime, this is supermoiré lattice constant is also way larger than the moiré lattice constant. So we can view this supermoiré as a modification of the potential on top of this moiré lattice. So specifically, how to do this moiré periodic approximation, we can view this structure by looking at the shift between the moiré 1, 2 and moiré 2, 3. So this shift is continuously and also periodic shifting over this supermoiré lattice. So across this supermoiré, this shift between moiré 1, 2 and moiré 2, 3, they are varying continuously. And at each position of this supermoiré lattice, we made this assumption that the local electronic structure can be approximatized very well by assuming this local shift is homogeneous across a whole 2D plane. And this resulting structure is moiré periodic. So we can apply this, so we can use a generalized continuous model to work out this moiré periodic potential. And then we average this local density of states over this supermoiré structure and average them over this different shift in the supermoiré structure to get a total density of states for the whole structure. So in the case space, the way we're doing this moiré periodic approximation is that you can, here I'm plotting the first Brillouin zone of layer 1, 2, and 3, labeled in blue, green, and red color. And the corner of the Brillouin zone is not collinear and that means that the whole system is not moiré periodic. However, if you stretch the middle layer, the green layer, a little bit, which will make the K point of the middle layer Brillouin zone shrink a little bit, you can make these 3 K points collinear And because they also have the same angle, this whole structure, the resulting structure, will be Moiré periodic. And you can write down this generalized Hamiltonian, and here the dt and dB are the absolute shift of A side of Moiré 1, 2 and Moiré 2, 3. And the difference dt minus dB is a relative shift, which you can see directly from this plot. So we can work out this Moiré band structure with a specific dt minus dB delta shift, and then average this shift on this supermoiré lattice. And here is the result. This is the density of state plotted against the x-axis is the energy, and the y-axis is the twist angle. This color is the amplitude of the density of state. As you can see, when you when we're close to the angle of 1.8 degree, this density of state show a very sharp peak close to Fermi energy, and it has a quite narrow bandwidth, and it's separated from the remote band by a region where there is a very low density of states, which shows that at this angle around 1.8 degree, the system possesses a very flat Moiré band in this Moiré-Brillouin zone, and that's what's the angle we aim for in our experiment. So from here, let me show you some of our experimental results. So we fabricate this device, and we use the electronic transport to measure the property. So the device structure is a helical trilayer graphene embedded in this BN dielectric. And we also fabricate this bottom graphite gate and top metal gate. So we can, by control these two gate voltage, we can control the carrier density and also displacement field independently. And here I'm showing some typical optical image of a few devices we studied. And the scale by is 2 micrometer. So here I'm showing the transport results. The left panel shows the longitudinal resistance Rxx, and the right panel showing the Hall density. And they are all plotted. The x-axis is a Moiré filling mu, and the y-axis is the displacement field. So here the Moiré filling is defined as a number of electrons per Moiré cell. As we can see this from this longitudinal resistance measurement, the structure, this helical trilayer graphene shows very large electron hole asymmetry, and we see at nu equals 0, we see this charge neutrality peak, and nu equals 4, which is a full filling of the Moiré flat band, we see this band insulator peak. And from this position, the density of this band insulator peak, we can extract the twist angle, which is around 1.79 degree for this specific device, which is very close to the magic angle, as I showed in the previous slide. So at nu equals 1, 2, and 3 integer fillings, we also see this resistance peak, which shows a strong correlation in this system. And this peak is correlated insulator states. This is also seen in this Hall density measurement, which also performed at 300 millikelvin. We can see at the nu equals 1, this Hall density has a dip, which shows this typical reset behavior, which is a demonstration of this strong correlation in the system. And this phenomenon is also very similar to what we have been observed in other Moiré systems, including magic angle twisted bilayer graphene. On the whole side, there's not much correlation, and we see this single particle Van Hove singularity. Quite surprisingly, if we go to the Moiré filling nu equals 1 or 3, and we perform this B-fast sweep, we see there's an anomalous Hall effect, which is manifest as hysteresis in the RxY together with this typical Barkhausen jumping. And this anomalous Hall effect, we see it at both nu equals 1 and 3. So here, this plot shows the result at nu equals 1. Here it shows the result at nu equals 3.1. And this is actually quite surprising. So before that, let me show some temperature dependence of this anomalous Hall effect. We did this temperature dependence, and we plot them using this so-called error plot to extract what is the Curie temperature of the system. and U equals 3, actually the Curie temperature of the system is about 10.5 Kelvin. And actually, by comparing with the literature, it's still the highest TC in any graphene-moiré system reported up to date. So from here, let me try to do some phenomenological reasoning. So first, as we all know, that the intrinsic spin-orbit coupling of carbon atom is very small. This actually means suggests that the anomalous effect we observed in this helical trilayer graphene can only coming from this orbital ferromagnetism. And the fact that the system has an orbital ferromagnetism actually suggests these Moiré bands carry a non-zero Chern number. Basically, they have a non-trivial topology. However, these raise two questions naturally. The first question is that how can a Moiré aperiodic structure have a Moiré bands? And the second question is how can a C2Z symmetric system have a Chern bands? The reason the C2Z symmetry is very important in this case is that if the system has a combine of C2Z and time reversal symmetry, this will actually means that system must have zero barrier curvature across in any place in the Brillouin zone, which means that the Moiré bands must have a trivial topology and must have a zero Chern number. So to answer these two questions, we find the answer actually lies in the lattice relaxation calculation. So because this carbon atom in this graphene sheet is actually not rigid, they can shift in X, Y, and Z to try to minimize the total stacking energy of the whole structure. So by performing this lattice relaxation calculation, we find the system actually relax into these big Moiré periodic domains, which we call them HHTG and H bar HTG. And they are actually separated by this Moiré aperiodic domain Waals, which is showing this red domain Waals here. And within each domain, the shift between this Moiré 1, 2 and Moiré 2, 3 actually stay at a constant. So this actually justifies the Moiré periodic approximation we have been using. And if we take a closer look of this HHTG domain or H bar HTG domain, you can find this Moiré 1, 2 and Moiré 2, 3, they are maximally shift and form this BN-like structure. Because they are lying at different Z, if you do a C2 rotation, HHTG will go into H bar HTG, but each structure is actually break the C2 symmetry, which opens a possibility for a non-trivial band topology. So here we also show this atomic stacking order within these H and H bar HTG domains, which is showing these three circles here. So with this lattice realization calculation, now we can think of the system better by just calculating the Moiré band structure at H bar HTG domains. Because these two domains are related by C2 rotation, so we can the density of state actually is same. So here let's focus just on HHTG domain, and here again is the density of state calculation plotted as a function of energy and the twist angle. So again, at the twist angle about 1.8 degree, we see a very sharp peak of density of states close to zero energy, with a very narrow bandwidth and separated from the remote band by a quite large gap. And this magic angle again is about 1.8 degrees. It's quite similar to the angle we found before, which is not very surprising. At this angle, we can calculate this band structure, Moiré band structure, in this Moiré Brillouin zone of this HHTG. And we can find it has this very flat band close to zero energy, which are separated from this remote band by quite large remote band gap, about 100 millielectron volts. And indeed, if we calculate the total Chern number of this flat band actually carry a total Chern number of plus minus 1 for K and K prime value. And if we add some artificial mass term to gap out this Dirac point at charge neutrality, we can actually find this valence and conduction band carries a Chern number of 1 minus 2 or minus 1 plus 2. Another thing I want to mention here is that if you use a so-called chiral limit to calculate the Moiré band structure, you can find this Moiré band is actually perfectly flat. And it perfect flat of this first Moiré band and at this series of the magic angle. So with this understanding of the HHDG, it's actually quite obvious for us to derive what is the Chern number for the H bar HTG because they are associated by C2Z rotation. C2Z rotation will also transform the value K to value K prime and also sublattice A to sublattice B. Therefore, for domain H and domain H bar, Ka and K prime B should carry the same Chern number. And so based on the Chern number calculation of HHDG, we can easily get what is the Chern number of the Moiré band in the H bar HDG domains, and is summarized in this chart. So basically Ka and K prime B of these two domains carry the same Chern number, same for the Kb and K prime A. So now if we plot this whole supermoiré structure, so here the color actually is the remote bandgap size times the total Chern number of one specific value K. We can see that the whole structure, the neighboring H and H bar carries the opposite value Chern number. So we call this and we call this system has a Chern mosaic, a mosaic of Chern domains. Forgot to mention that the total band degeneracy of the first flat band is 8, which account for the valley, spin, and sublattice also Chern degrees of freedom. A natural next step will be to think about the correlated physics because so far I've been showing you the single particle calculation result, and to see what is the correlated ground state at integer fittings. And this result has been summarized in this paper by our Curie collaborator, and where they did the strong coupling and also Hartree-Fock calculation. So here I'm just simply show you an example of a Hartree-Fock calculation specific at nu equals 3, close to magic angle with this parameter. And here I'm showing what is a band calculated at this spin down sector, which you have 4 bands in total in this Moiré flat band. And the 3 bands are filled because we are nu equals 3, and the 1 band you can see is shift up in energy in this Hartree-Fock calculation and is fully empty. So here the color actually means a Chern, also sublattice polarization, and we can see this unfilled band has a same sublattice polarization across this whole Moiré-Brillouin zone, which means that it's carrying a net total Chern number, which suggests that nu equals 3, we have a Chern inserted. The similar result is also seen at nu equals 1. So with this, we think we understand what is the origin of this anomalous Hall effect from in this structure. Another thing I want to briefly mention here is that compared with twisted bilayer graphene, these helical trilayer graphene bands are more rigid against this Hartree renormalized dispersion, which makes this strong coupling calculation result more robust in this when you account for this correlation. With this calculation, actually, we understand what is the origin of these correlated states and also the anomalous Hall effect, the orbital magnetism, and actually we can try to understand more in detail our transport result. And one of the example is this the observed topological phase transition introduced by this displacement field. So in this first panel, I'm showing the Hall resistance measured anti-symmetrized at plus minus 60 millitesla. Because this field is very small, so the Hall resistance is dominated by the anomalous Hall effect instead of the regular Hall effect from in magnetic field. So the hotspot here actually shows the distribution of the anomalous Hall effect as a function of filling and also displacement field. And the right panel is nothing but just a longitudinal resistance plotting the same region. As you can see, this anomalous Hall effect First of all, it happens at nu equals 1 and 3, but it has a certain displacement field dependence. At a high displacement field, this anomalous field is disappearing. However, in this longitudinal resistance, we can see this all the correlated feature at nu equals 1, 2, and 3. They have this correlated gap is closing at a certain displacement field, but at nu equals 1 and 2, we can see that the correlated gap reopen at a higher displacement field. While at this higher displacement field, we don't see any anomalous effect. This can be captured in this Hartree-Fock calculation when we introduce this displacement field. So here the displacement field is modeled by this interlayer potential difference U. And here when we increase U, we are basically increasing the displacement field. And as you can see at here, still it's an example at nu equals 3, but nu equals 1, the situation is very similar. And nu equals 3, when you increase the displacement field, around this critical displacement field, there is a band inversion happen for this unfilled flavor. And after this band inversion, at this high displacement field phase, we can see the sublattice also Chern polarization of the band is changed. And now the band is actually carry a total Chern number equal to 0. Therefore, at this high displacement field phase, even though we still have this correlated and flavor polarization, because the total Chern number is 0, we don't see any anomalous effect. So far I have been telling you about the physics, which kind of dominated by a single domain, H-bar or HTG. And from here, I want to briefly show you some of the some inter-domain or domain wall physics we're seeing associated. So basically, this Chern mosaic physics. So here is a measurement in our HTG device, and the measurement is done by varying the magnetic field, perpendicular magnetic field, and also the filling around nu equals 3 at a fixed displacement field. And the difference between these two plots is just that we are sweeping density down or sweeping density up. And here the magnetic field is a slow axis. So as you can see there, when we sweep density up and down, we see a big hysteresis close to 0 field at a field when the field is less than this critical field about 200 millitesla. And this is strikingly similar to another system, which is measured by other group, which is a near commensurate HBN MATBG superlattice. In this system, the optimum at nu equals 1, the system is also optimal magnet. So they see this anomalous effect. And when they did the same kind of measurement, they see this big hysteresis upon switching density. And this device has been later imaged using the scanning squid, and the scanning squid result showing that the system is actually a Chern mosaic. So by comparing this transport result, does that mean actually that also this transport also suggests that our system is also a Chern mosaic system? I think our answer is yes. And in the following slides, I'll show you our picture about how to explain this transport behavior. So to understand this transport behavior, I think we need to answer two questions. The first is why this switching behavior is happening. And second is that why this switching behavior only happens below this critical field about 200 millitesla. So to understand why this switching behavior is happening, we need to think about the total magnetization of the system. The total magnetization of the optical magnets has two contributions. The first is the self-rotation magnetization, which accounts for the self-rotation of the wave packet. And the second is the Chern magnetization, which you can think of it as account for the center of mass motion of the wave packet. And the total magnetization is the sum of these two contributions. And as you can see, when you cross the gap, this Chern magnetization will acquire a contribution, will acquire a value, and which usually have the opposite sign as the self-rotation magnetization, which may make this total magnetization switch sign when you cross the correlated gap. And here we did this calculation at nu equals 3, where we see this electrical switching behavior. So here I'm showing this Hartree-Fock band again, and this dashed line is the original band without Hartree-Fock potential, and this blue band is the Hartree-Fock band. As you can see, this Hartree-Fock is the effect mostly shifts the band rigidly, and u equals 3, this K prime up sector is fully filled, and this K prime down sector is half filled. And by doing this assumption, we can calculate this total magnetization across this nu equals 3. And you can see indeed this total magnetization switch sign for this K for K prime value.
Li-Qiao, I think we have like 2 minutes left.
Yeah, I think I'm wrapping up.
Okay.
So yeah, thank you. So the K value will actually have the opposite sign of the will carry the opposite sign on this total magnetization. Therefore, when the system is doped across this nu equals 3, the system will actually tend to polarize from K prime to K value to minimize its total magnetization Z energy. And this is the first order phase transition, which will give us this hysteresis when we sweep the density. And to understand why this switching only happens at low field, we need to think about what is the flavor polarization situation for H and H bar domain, basically this interdomain physics. First of all, these sublattice and Chern degrees of freedom are imprinted because of the stacking order of the system. So let's say if H domain is polarized into A sublattice, the H bar must polarize into B sublattice. And spin degrees of freedom is also not important here because the spin doesn't change the Chern number. Then the only degrees of freedom we're considering here is the value. So we have good reasons that the Chern domain walls are favored. So basically, this interdomain exchange, this value tend to polarize into the same value across the whole sample, because the interdomain exchange energy is not impossible between the opposite values. So when the system tend to polarize in the same value, which will actually give us this staggered opposite Chern number, which is labeled red and blue here. So the system, as I explained, as I mentioned, is a Chern mosaic. And we label this, when the system polarizes all into K value, we label them as an alpha state. And when it's all at K prime value, we label them as an alpha prime state. And when at high field, when the filling is less than nu equals 3, the system tend to polarize into one specific geometry. Let's say it's alpha here. And when you increase the doping across the nu equals 3, as I said, the total magnetization may reverse sign. So the system tend to polarize into the opposite value to minimize its total orbital Z energy. And when you, therefore, it goes to the alpha prime state. However, at low field, this reversal doesn't happen because we think this orbital Z energy is less than some pinning energy of a valid pinning energy of the system. Therefore, that's the reason we see this hysteresis as this low field range. So this is a picture we have about this Chern domains, and we think it accounts for our result well. So lastly, let me quickly briefly mention also that we see this anomalous effect also at nu equals 2/3. As you can see, there is a very weak hotspot showing here, apart from this nu equals 1 and nu equals 3. And when we do this BFAST, we do see this hysteresis, the anomalous effect at 2/3, but we don't see a nu equals 1, which shows that it's actually a separate phase at this fraction field. Because we don't have quantization of due to this domain wall, we don't know what is a Chern number specifically, but we think the possible ground states could be a fraction of translator or topological charge density. So lastly, let me quickly summarize. Hopefully, I convince you that this helical trilayer graphene is a system with strong correlation and robust Chern physics. The latter is actually enabled by this C2Z symmetry breaking on this Moiré scale. It also has the supermoiré domain physics and may have potential exotic physics. I want to advertise that all of the results I show in this talk has been summarized in this paper we posted in archive recently, and you're welcome to look at it for more detail about this project. And with that, I would like to thank for your attention, and welcome to any questions.
Great. Thank you very much, Li-Qiao. So if anyone has questions, you're welcome to raise your virtual hand, and you can just ask freely. And then there are a few questions posted in the chat. So let me take a look by order. So the first question is, when broken the domain of ferromagnetic M, new phonon create in the lattice, then what is interactions between the lattices? And the same person asks, show new data of raising the phonon wave function after domain broken. Maybe Sarfraj, you can clarify in your own words, if you can. Okay, Li-Qiao, unless you, if you understand
the question is about the phonon in the system. We didn't think about it much, but so when you say the broken domain of ferromagnetic, I'm not sure if the phonon is coupled to the magnetic states here. It's not obvious to me if that's what you're asking. Yeah, therefore, in terms of like this ferromagnetic is formed at these integer fillings, I'm not sure if that will change the phonon spectrum, if that's what you ask. The second question is, thank you for the presentation. Does the orientation and the flexibility of the graphene sheet affect the conductivity of the electrical current? Yes. The flexibility, actually, this lattice relaxation is a manifestation of this flexibility, right? So if we think the structure is rigid, we actually think the system is more aperiodic. It's become more periodic because of it's actually flexible and move each atom, carbon atom, move a little bit to minimize the total stacking energy, and which result in these more periodic domains and change the whole band structure, and that definitely is affecting this electrical conductivity. Do you think if the magnetic domain effect is correlated to the Earth's magnetism, or is far-fetched? Yeah, yeah, to be honest, I'm not a expert of this Earth magnetism. I'm not sure if it has any domain physics, but maybe there are better people to ask, for example, some people working in this Earth physics.
I think the question may be, is the Earth magnetic field affecting your sample?
Oh, then we are pretty sure it's not, because I think Earth magnetization is less than 1 millitesla. It's like few Gauss, if I remember correctly. And the magnetic field required to reverse this magnetic domain is 100 millitesla. It's on the order of 100 millitesla, which is way larger than the Earth's magnetization.
Okay, any other questions? Okay, if not, let's thank Li-Qiao again for this wonderful talk. And let me, before you leave, just remind you of the next seminar, which will take place on Tuesday, January 9th, where we will hear from Ling Fan from the Department of EACS at MIT. So this concludes today's seminar, and thank you all for joining today, and I hope we'll see you on January 9th.
Thank you for attending.